In this video lecture, we are going to continue to talk about source-free RL and RC transient circuits. In the last class, we saw that if you have a capacitive circuit or an inductive circuit with a sudden change in the circuit at time t0, where the sources are removed at t0, what happens is that the energy stored in the capacitor or the energy stored in the inductor will cause current to flow in whatever resistors are remaining, and eventually all that energy will be dissipated. And what happens is all the voltages and currents in the circuit follow an exponential decay and eventually fall to zero, and it takes 5 time constants for that to happen. In today's lecture, we're going to formalize this with an algorithm that goes step by step through the process. We will then do lots of examples. So here's the general solution algorithm for source-free RC and RL circuits with, once again, no source present after T0. The first thing you want to do is solve a DC steady-state circuit by finding the voltage across the capacitor or the current through the inductor before the discontinuity. The next thing is, depending upon what the question asks for, you also want to find the value of some variable x right before the discontinuity. If x was some other voltage or current in the circuit different than VC or IL, you have this step. This particular step 2 you may not have to do. We'll talk about that when we go through some examples. The next step is you redraw the circuit after the discontinuity, and of course the voltage source and current sources are now going to be gone. The next step, as we saw in the previous lecture, is we know that 2 key variables cannot change instantaneously: the voltage across the capacitor in an RC circuit or the current through an inductor in an RL circuit. So you set VC of T0 plus equal to VC T0 minus, or the same thing with IL. The next thing we do is whatever circuit remains from step 3, we want to simplify it by Thevenizing the circuit around the capacitor or the inductor so that all that you have is either a capacitor and a Thevenin resistance, or an inductor and a Thevenin resistance. Once you do that, you can then utilize our results from before, knowing that the time constant is either going to be R Thevenin times C or L over R Thevenin. We also know from step 4 what our initial conditions are. We can finally put those together to get our decaying exponential that we know has to happen. The voltage across the capacitor has to be VC naught, which comes from step 4, times e to the minus t naught over tau, where tau comes from there. Likewise, if it's an RL circuit, IL naught comes from step 4, and the time constant comes from that expression. Step 6, like step 2, is a step that you may or may not need to worry about. If the problem is asking for either VC or IL, we are done after step 5. But if the problem is asking for some other voltage or current in the circuit, what we then need to do is to find a general expression for whatever variable we're looking for in terms of VC and IL, which we have from step 5, and then use that to determine our equation for whatever variable x that we're looking for. So as I said, step 2 and step 6 are steps that we may or may not need, as we're going to see in some examples. We can finally put everything together, and we're going to have 2 regions of operation. Before the discontinuity, this is our DC steady state. We're going to have some constant value for whatever variable we're looking for. After the discontinuity, this is our transient part of the circuit. We're going to have an exponential decay from some initial value all the way down to 0. One comment about here, depending upon what our variable x is, you may or may not have a discontinuity at time t0. For example, if we're looking for VC or IL, we know that we cannot have a discontinuity there, but we will see in some examples that for other values of x, you possibly could. Anyway, if you think about this problem, there are really only 4 key pieces of information. One is the initial value in DC steady state of whatever variable we're looking for. Second piece of information is the time of the discontinuity, and that's typically given in the problem. The third piece of information is the value of our variable right after the discontinuity. Once again, depending upon the variable, we may or may not have a difference in x of t0 plus and x of t0 minus. The fourth piece of information is how long it takes for the exponential decay to go to 0. And this, of course, is related to tau. Specifically, it is going to be 5 tau. All right, let's look at some examples. So this is a circuit with an inductor, multiple resistors, a current source, and a switch. So at time 0, the switch is going to open, and the current source is going to be removed from the rest of the circuit, which means whatever energy is stored in the inductor due to the current source, at time 0, it will slowly start dissipating through the resistors. So the first step in solving this circuit is do the DC steady state circuit for t less than 0. So we have our current source, a resistor there, a resistor there. The inductor itself is a short circuit in DC steady state, and a resistor there. 150 ohms, 50 ohms, 200 ohms. The first thing we need to find then is IL of 0 minus. If you look at this current source, it basically has 2 paths that it can go. It can either go through the 150 ohm resistor, or it can go through the 50 ohm resistor and then through the inductor. Notice, because the 200 ohm resistor is in parallel with the inductor, which is shorted out, no current will flow through the 200 ohm resistor in this example. So IL of 0 minus we can now find from current division. It's the total current times the opposite resistance, 150 ohms, over the sum of the 2 resistances, 150 plus 50, and that equals 15 milliamps. Step 2 now is to find x of t for t less than 0. But in this case, x of t is IL of t. So step 2, we do not need. Step 3, we want to redraw the circuit for t greater than or equal to 0. Now, the current source is gone. We still have our 150 ohm resistor. We still have our 50 ohm resistor. The inductor is no longer a DC short because we're no longer in DC steady state, which means this resistor here on the right, this 200 ohm resistor, is going to play a part again. So you redraw the circuit after the discontinuity. Step 4 is a pretty trivial step. We know that IL, so we're solving for IL of t, we know that IL of 0 plus is going to equal IL of 0 minus, which is going to be 15 milliamps. Why do we know that? Because the current through the inductor cannot change instantaneously regardless of what happens to the circuit. Step 5 is to find the Thevenin equivalent resistance as seen by the inductor. So if you look at this inductor down here, it doesn't know that it's connected to a 200 ohm resistor on one side and a 150 and 50 ohm resistor on the other side. What it sees is that it is connected in parallel to a 200 ohm resistor and 150 and 50 ohm resistor in series. So what the inductor sees is a 100 ohm resistance. That's 200 in parallel with 150 plus 50. From here, if we wanted to, we could write the differential equation for the circuit, but we actually don't need to. We know what the result is. We know the result is going to be a first order constant coefficient differential equation, and we know that the response is going to be an exponential decay. So all that we really need to do is to find tau. Tau is L over R Thevenin, so 0.2 millihenry divided by 100 ohms, or 2 microseconds. And then we can put everything together to get the current through the inductor is going to be 0.015 e to the minus t over 2 times 10 to the minus 6 amps for t greater than or equal to 0. We can finally plot this. We have our DC steady state value of the current through the inductor. And at time 0, it's going to start decaying exponentially, and it's going to take 2 microseconds times 5, or 10 microseconds, to get to 0. So it will decay like that. 5 time constants. Finally, step 6, like step 2, is not needed. Why is it not needed? Because the x of t we're looking for is IL of t. In this problem, it's identical to the problem before, except for what we're looking for. Now, rather than looking for IL, we're looking for IX. So the only differences here is steps 2 and step 6. So 2 additional things that we need. First off, we need to find IX at 0 minus. That is our step 2. We also need a general equation relating IX of t to IL of t for t greater than or equal to 0. That is step 6. So in step 2, Ix of 0 minus we can find as follows. We have a 150 ohm resistor there, 50 ohm resistor, 200 ohm resistor. Here's IL. and this now is Ix. As before, this 200 ohm resistor on the right is shorted out, so Ix of 0 minus, once again we can find from current division, the 20 milliamp current source basically either goes through that branch or it goes through that branch. So Ix of 0 minus is 20 milliamps times the opposite resistance, in this case 50 ohms, over 150 plus 50, or 5 milliamps. In step 6, this is for t greater than or equal to 0, we have this situation. (150 ohm resistor, 50 ohm, 200 ohm. Here's our inductor with the current IL. What we want to do here is find an expression for Ix in terms of IL. A way to do this is to think of the inductor as a current source. In many ways, the inductor is a current source. It has this energy from before the discontinuity, and that energy is now being used to drive the circuit. So if you think about this inductor as a current source, you can find Ix once again from current division. The current coming out of the inductor IL has two options. It can go through this branch, or it can go through that branch. So from current division, Ix of t is equal to negative IL of t times the opposite resistance over the sum of the two resistances. The reason for the minus sign is because Ix is defined as the current going through the 150 resistor from top to bottom, but IL, because it goes from top to bottom through the inductor, is going to be coming up through the 150 ohm resistor. So we can now formulate our final answer. Ix of t is going to be 5 milliamps for t less than 0. We got this from step 2. And for t greater than 0, if we look back to this problem here, we knew what IL of t was. Ix of t is just negative IL of t over 2. So it's going to be minus 7.5 e to the minus t over 2 times 10 to the minus 6 milliamps for t greater than or equal to 0. If we were to plot Ix of t now, we see that it's 5 milliamps here. At time 0, it goes all the way down to minus 7.5 milliamps, and it still decays to 0 in 10 microseconds. The big difference we see from the previous case is that here we do have a discontinuity. Whenever our variable x is something other than IL or VC, there's a possibility of having this discontinuity. Doesn't have to happen, as we'll see in some examples, but it can happen. So we saw this problem in the last lecture with the capacitor, a couple resistors, and a voltage source. We are now asked not to find the voltage across the capacitor, but we're asked to find the current through the capacitor and the current through the resistor R2. From before, what we have is the voltage across the capacitor for t greater than 0 was R2 over R1 plus R2 times Vs times e to the minus t over R2c volts. This was for t greater than or equal to 0. To get IC and IR, basically we got to look at step 6 and find an expression relating those variables to what we have, Vc of t. IC is pretty simple. The current through a capacitor is always C times the derivative of the voltage across the capacitor. So we get C, the derivative of this expression here is going to be minus 1 over R2C times R2 over R1 plus R2 times Vs times e to the minus t over R2c. This c cancels with this one, this R2 cancels with that one, and we end up with minus Vs over R1 plus R2 times e to the minus t over R2c. Amps. Whoops, I accidentally wrote V, I meant A. IR of t is the current through R2. IR of t is just VR over R2, but VR is VC. So once again, we can express IR in terms of VC. And what we see here, it's plus Vs over R1 plus R2 times e to the minus t over R2c amps. What we note here, as expected, IC of t is equal to minus IR of t. Because for t greater than 0, they really are the same current, just going in opposite directions. If we were to plot these, we saw that Vc of t started like that, and then at time 0 we had our exponential decay, and I am plotting it now in a normalized time, so t over tau, so it always goes to 0 at 5 now, because that's 5 time constants. We saw that Vc of t looked like that. We saw that IC of t, IC of 0 minus was 0 amps. Remember, the current through a capacitor in DC steady state is 0. So this would be 0 amps. Then at time 0, it goes to minus Vs over R1 plus R2. And then decays back up to 0 in 5 time constants. Notice no discontinuity there, but there is a discontinuity here. Once again, for variables other than Vc or IL, you could possibly have a discontinuity. For IR of 0 minus is Vs over R1 plus R2. Where does this come from? If you look at the circuit before the switch is thrown, we have that, and it's just Ohm's law. IR is Vs over R1 plus R2. What happens at time 0 is it's going to be Vs over R1 plus R2 times e to the minus t over R2c. It's an exponential decay. Takes 5 time constants to get to 0. And we saw in this case, just like with Vc, there is no discontinuity at time 0. No discontinuity in IR of t at t equals 0. The reason being is because IR is equal to VR over R2, which is equal to VC over R2. Since VC doesn't change instantaneously, IR cannot change instantaneously. In all the examples before, the change in the circuit at T0, usually at 0, has been a switch removing the sources from the circuit. It turns out that that is not the only type of change you can have. In fact, there are two common ways to model the abrupt change in the network. The one we looked at before is the switch. That models physically removing the source from the circuit. But how about turning the source off? To do that, we need to use a different mathematical model, the unit step function. Let's review the unit step function very briefly. U of t is defined to equal 0 when t is less than 0 or 1 when t is greater than 0. In other words, you look at what's inside the parentheses here. If it's positive, unit step function is 1. If it's negative, it's 0. So U of t itself looks like 0 and jumps up to 1 at time 0. U of minus t does the exact opposite. This would be sort of turning off. It's on, and then it turns off. You can also have a delay, so U of t minus 5, for example, turns on at 5. Just remember that whatever is inside the parentheses, if that is greater than 0, you're on. If it's less than 0, you're off. We're going to see that this unit step function is very useful for modeling sources that are turned on and off as opposed to being switched out of a circuit. We're going to see that in some ways they're very similar, but in some ways they are very different. Here's a simple example. Suppose you have a current source with a parallel resistance switched out of the circuit at time 0. Compare that to a current source and a parallel resistance turned off at time 0. So this is switched out at time 0, and this one is turned off at time 0. For t less than 0, they are identical. As far as the rest of the circuit is concerned over here, these two look the same. But for t greater than 0, an open circuit at this point because of the switch opening up. But in this case, the open circuit is here because the current source value is equal to 0 amps, or an open circuit. The difference is with this resistor over here. In the top case, that resistor is not going to be seen by the rest of the circuit. In the bottom case, that resistor will be seen by the rest of the circuit, which means it has an effect on things such as time constant, voltages, and currents. This will be illustrated in this example here. If you look at the previous RC circuit, we've seen this circuit a couple times now. It's the same circuit as before, except now, rather than having a switch over here, we're going to use a unit step function to turn the voltage source off at time 0. And we're going to see how this changes some of our answers. So we're going to see that there's no change for t less than 0. In other words, Vc of 0 minus is still R2 over R1 plus R2 times Vs. We're going to see that IC of 0 minus is still 0 amps. And we're going to see that IR of 0 minus is still Vs over R1 plus R2 amps. For t greater than 0, however, we see a big difference from before. So now, because of this unit step, the voltage is going to be 0, but the voltage source is still there. R1, R2, and our capacitor. So in this case, the Thevenin resistance seen by the capacitor is the parallel combination of R2 and R1. So our new time constant is going to be R1 times R2 over R1 plus R2 times C. Before, the time constant was just R2C. Now it's this more complicated expression. So how does this affect Vc, IR, and IC? Vc only changes in that time constant. So Vc of t still R2 over R1 plus R2 times Vs times e to the minus t now over this tau nu. The only change from before is the time constant is different. Likewise, IR of t, which is just Vc of t over R2, also changes only by that one term. So it is Vs over R1 plus R2 times e to the minus t over this new time constant. IC of t, however, changes even more. IC of t, we know, is C dVc dt. So it is going to be C times the derivative of this. The derivative of this is minus 1 over tau nu times R2 over R1 plus R2 times Vs times e to the minus t over tau nu. 1 over tau nu is R1 plus R2 over R1 times R2 times C. So this cancels with that cancels with that, and that cancels with that, and you end up getting negative Vs over R1 times e to the minus t over tau nu. So now, not only is this different from before, but this is different from before. The other thing we see is that IC of t no longer equals minus IR of t for t greater than or equal to 0 because of the presence of R1. Our final example is going to be a little bit different. This example is one where we're going to work backwards. In this problem, we are given the response of the voltage across the capacitor. What we don't know this time is the value of the resistor or the amplitude of the current source. What we want to do in this problem is use information that we can gather from this plot to determine those two values. To get R, we want to use our knowledge about the time constant. We know the time constant is R times C. The capacitance we know. We also can find the time constant two different ways in this problem. One way is you look to see when this response goes to 0, it takes 10 milliseconds. So the time constant is going to be 10 milliseconds divided by 5. remember that it always takes 5 times the time constant to decay to 0. So tau would be 2 milliseconds. You can also see it, though, from looking at this initial slope. If you remember, one of the properties of the exponential decay is if you extrapolate the initial slope down to the x-axis, it hits the x-axis at tau. So whether you use that approach or that approach, you find that the time constant is 2 milliseconds. So the value of the resistance now is going to be tau over c. So 2 times 10 to the minus 3 over 10 times 10 to the minus 6, or 200 ohms. To get the value of Is, we're going to look at this initial value here. At t equals 0 minus, the current source is on. Its value is Is. You have a resistor R, which we now know is 200 ohms. And the capacitor is an open circuit. We know that Vc of 0 minus from the plot is 20 volts, but that also has to equal Is times 200 ohms. So Is has to be 20 volts over 200 ohms, which equals 0.1 of an amp. So at this point, we've now determined the value of Is and also the value for R. Next lecture, we will look at driven RC and RL circuits. Those are circuits where you still have discontinuities at some time, 0 or another time, but now, rather than having no sources present after the discontinuity, we will have sources present. It's going to add one little wrinkle to the solving of the circuits. It's going to add a couple steps to the algorithm, but it really is going to follow, for the most part, the same process we've been doing. Have a good day.